Hello, I'm Prajakta Karandikar, and I shall be presenting my project for the course Pattern Recognition under Dr. Depang Wu. This is a fingerprint recognition system involving minutiae extraction and storage in database and matching against it for identity authentication. I shall begin by explaining the problem domain. A fingerprint matching system has great applications when subsumed in everyday authentication systems, and unauthorized personnel can get access to passcodes and PIN codes, thus making these conventional security features less reliable. Use of biometrics is a way around this problem. For example, there are face recognition, speech recognition, fingerprint recognition systems in place. They make use of an individual's unique features to enforce security. Fingerprint analysis systems are widely used today in areas of system securities and crime prevention. Many modern devices too support these desirable features. These are the relevant terminology for this project. This biometrics, minutiae, ridge ending, bifurcation, noise reduction, class 1 detail, class 2 detail, or also referred to as minutiae, class 3 detail, and the key concept to this project, which is score point localization. These are the diagrams explaining the various feature levels of minutiae. The common approach. The following stages entail a typical fingerprint analysis system. First comes pre-processing. The steps are sensing the data via sensors, image enhancement, background elimination and thinning, and binarization of the image. The next step is extraction of minutiae. Minutiae detection is the most crucial step, and then comes creation of database. Then comes post-processing steps, which involve removing false positives and authenticating. This is the diagram depicting the entire process. Image pre-processing. We first use several pre-processing steps on the binary image in order to eliminate the spurious lakes and dots and to reduce the spurious islands, bridges, and spurs in the initial image. By removing all these buggy pixels introduced at the thinning stage, our algorithm can detect a maximum number of minutiae from the fingerprint. This allows the true minutiae preserved and the false minutiae removed in the later post-processing stages. Image enhancement techniques used for improving the quality of digital images by manipulating them with software in order to improve the extraction process complexity, by making it lighter or darker, and by changing the contrast. Contrast improvement is a useful aspect in fingerprint analysis image processing. There are multiple techniques of enhancing an image to suit a particular application. Image enhancements can be point-based or mask-based. We consider point-based systems here. There are multiple point-based methods such as image negatives, contrast stretching, which is a key aspect, thresholding, brightness enhancement, log transformation, and power law transformation. Contrast stretching. It is the most commonly used technique as it involves contrast ratio of an image. It expands the range of intensity levels of an image, and it can be done in one of the three ways. The first would be multiplying each input pixel intensity value with a constant scalar value, where O is the output pixel, P is the input pixel, and I is a constant. We can also use a histogram equivalent of the image to improve contrast. And the third technique would be to apply a transform function which makes the darker portions darker and bright portions brighter by assigning slope values based on threshold values of brightness. Ridge thinning. We apply algorithms to bring down complex images to eliminate unnecessary pixels till the ridges are just 1 pixel wide. There are serial and parallel thinning algorithms. We use iterative parallel thinning algorithms because of their efficiency. Single points, whether there are single point ridges or single point breaks in a ridge, are eliminated during this process. Centroid-based thinning algorithm. This is one of the widely used algorithms. It checks the 9 by 9 local neighborhood around a pixel to retrieve the centroid pixel, and the other pixels are removed. This process is performed iteratively until less than 10 pixels are deleted in a loop. To ensure the ridge is 1 pixel wide, a post-processing loop is carried out which deletes these pixels, satisfying some given precondition. The image on the left is the original image. The image on the right is a thinned image. Image binarization. True information that can be extracted from a fingerprint in a binary form along with the ridges and valleys. It's a very important step in the process of ridge extraction. It transforms from a 256 level image to a 2-level image that gives the same information after processing the data. The image is divided into 16 by 16 blocks, and the mean intensity value is calculated for each of those blocks. Each pixel is then turned into 1 if its intensity value is larger than the mean intensity value of the current block to which the pixel belongs. If not, it's not. Extracting minutiae requires a laid foundation groundwork leading up to such a image specimen from which the extraction of fingerprint details is simplified. The given steps 1 to 4 here, they are the process leading up to step 5, which is securing minutiae position and orientation of the absorbed points. This is the final step of the extraction phase. The process of minutiae extraction involves the use of MATLAB functions to operate on the obtained data from the pre-processing. This data is binarized. The background is eliminated and only the information points are maintained. This simplifies the minutiae extraction part to a great deal. The focal points after the image pre-processing are the individuality of the image, the uniqueness of the fingerprint. These points are used to compare two fingerprints for their similarity or dissimilarity. The minutiae extracted may include many spurious minutiae and may degrade the accuracy of the matching system if they are considered to be genuine. Here I have explained the procedure for identification for the false minutiae and the removal of the same by assuming a threshold distance d as the average inter-ridge width, representing the average distance between two parallel neighbor ridges. In the fingerprint pattern, the bifurcation and termination are considered in the same ridge if the distance between the two is less than the threshold distance d, and removed the bifurcation and termination. By identifying two bifurcations, if any, on the same ridge with the inter-ridge distance less than the threshold value, the two bifurcations will be removed. If a false minutiae due to any two terminations are identified with the following conditions: the first, two terminations are within the distance d and their directions are coincident with a small variation in angle, and 2, no other termination is located between the two terminations and the identified false minutiae by the broken ridge due to the two terminations are removed. These two terminations located in a short ridge with a distance less than d are then identified and removed. Creation of the database. Up to now, when a new fingerprint image is added to the database, the minutiae details were calculated twice, once for the input image and the second for the image rotation, in order to make the process rotation invariant. The image was rotated using the MATLAB function IamRotate. When a new fingerprint image is added to the database, only one core point is found using core point localization techniques. Authentication of a rightful user to give access to his confidential information is the essence of this project. Authentication is an absolutely essential element of a typical security model. It is the process of confirming the identification of a user that is trying to log on or access resources. There are a number of different authentication mechanisms, but all of which serve the same purpose. Comparing feature points. T and I are supposed the template and the input fingerprint to match. The position and the orientation of the minuity points were already stored separately. We assume that I and T had different number of feature points, supposing M and N, such that T is from M1 to Mn and I is from M'1 to M'N. The two minuity points Mi and M'J are considered to match for T and I if their position and orientation are close. Using the spatial distance Sd and the direction difference Dd, the formulas for which are given here. The T1 and the T2 found in the previous formulas are the two tolerance parameters that we can adjust. Those inequalities come from the classic Euclidean distance in 2D and the circularity of angles. The function MD determines the closeness between the two given points. Finding transformation y equals map of x for all the points in x in the 3D space. It returns another point y. But there has to be a corresponding relation between the input and the template points. For each of the input point image in T, there has to be an I template point, which is a matching point. The preliminary observation of the system. The input fingerprint image is enhanced. Rich thinning is achieved. A small region of the output is taken to show the fingerprint clearly, which may also be called sectorization. The extraction of minuity from fingerprints is achieved. The background is removed and only the information points are saved. The overall system observation. This system is standalone in terms of an image extraction to image matching range of processes. Also, the graphical user interface makes it easy for a user to operate these functionalities. The system currently saves the extracted image's minuity into the database and can retrieve a match for a given input file if it's present in the database. If not, the distance is larger than a pre-decided permitted value and it indicates that it's not a match. It shows the match in terms of distance. The lower the distance, the better the match. The possible future enhancements for this project. The pre-processing steps to eliminate noise can be improved, and this can give better matches. The output is in terms of distance between the given two entries, one being the input and the other being the closest match from the database. A threshold can be applied as per the suitability of the given application. The graphical user interface can also be made more sophisticated. Here, I would like to extend my gratitude to Professor Dr. Dipang Oliver Wu for his continued guidance during the course of this project. His knowledgeable insights into everyday problems related to pattern recognition are a stimulus of interest and scientific curiosity for us students. The content and concepts of the course have been very useful to prepare ourselves for the industrial applications also. I would like to now give you a demonstration of the project. FB is my main file. This is the graphical user interface that I have developed. Here we have the options on the right hand side panel for load model, addition to the database, for system recognition and cleaning the database. First, we clean the database of any pre-existing models. It is already clean. The panel that you see in front of you, there are 4 boxes. The first one would be the original image that we load. The second would be after the background removal. The third would be the binarized image. And the fourth would be the core point localization. For example, I'm loading a model. I have a database of fingerprints. I'm loading the first one. The first box is the original image. The second is with the background removal. Here they have identified the core point localization, and this is the binarized form. I would like to add this to the database. This fingerprint was added successfully. I would like to perform this operation 3 more times to add multiple fingerprints. After loading the model, I'm adding this to the database. I'm doing this for one last time. Now that we have enough models in the database, we try performing a system recognition. For that, we again need to load a model. First, we try comparing the database with a model that is not present in the database. We perform a system recognition here. The distance is given to be 2529. This is the nearest distance, which is way above any threshold value, which indicates that the fingerprint is not present in the database. We now try performing it for a fingerprint that is present in the database. We load the model. We perform a system recognition. The nearest fingerprint is number 4 with the distance of 0. This means that this image is present in the database and it corresponds to image number 4, and the distance between the two is 0, which is a perfect match because it was the same image. The system would find applications in safeguarding access of only authorized personnel and saving their fingerprint models in a database. When a new user tries logging in, his or her fingerprint model is matched with the database. If the nearest distance found is greater than the threshold value, the access is denied. It cannot always be 0 each time due to the difference in position, orientation of the finger placement while scanning. So a reasonable threshold must be secured. Thank you for watching the presentation.